It's commonly said, at least on YouTube, that Enigma was broken because it couldn't encrypt the letters itself. If you press A, you'll never get A in the ciphertext. This means, if we try to guess what's in the message and even one letter's the same, then it can't be a match. Well, this helped. I don't think it was the key to breaking Enigma. I'm Matt Regan. I have a PhD in computer science, but I actually think what I'm about to go over in this video should be taught in Computer Science 101.
It's over 150 million possible settings.
Very good.
159, if you want to be exact about it. 159, with 18 zeros behind it.
What really cracked Enigma was the BOMBE's ability to narrow down the search for plugboard settings. Instead of 150 million possibilities, it just had to search through 26 per rotor setting. I made the claim in my last video, and now it's time to put up or shut up. Before we can truly understand how the BOMBE works, we need to grasp the problem that it's designed to solve. In this video, I'm going to try to write a simple software routine to do just that. If it works, in the next video, I'll transfer the design onto an EEPROM-based BOMBE replica. There are two main forms of the BOMBE, the basic BOMBE and the enhanced BOMBE, which has a Welshman diagonal board. I'll go over the basic BOMBE first. Here's the replica of the BOMBE built by Alan Turing and his team at Bletchley Park. We can see all of these rotating drums. Each group of 3 drums represents a single Enigma, right rotor on the top, left rotor on the bottom. We have 12 Enigmas per row, so a total of 36 Enigmas for the whole machine. While they all advance in lockstep, they can all be programmed with differing initial rotor settings. If we want to, we could start this one at NSX, this one at NSY, NSZ, NSA, NSB, and so forth. So they're all offset by one position, but other combinations are possible. What this allows us to do is effectively unroll the encryption loop, so that here, the characters of Veta Forsaga Biscaya can be encrypted or decrypted in one step. While in practice, we don't necessarily need to encrypt all the letters of Veta Forsaga Biscaya at once. This ability is critical to the algorithm. Now, to break Enigma using a BOMBE, we not only have to accurately guess what the encrypted message contains, but where it occurs in the message. It turns out the most commonly used text to crack Enigma were Veta Forsaga, which is weather forecast, and Kleine Besonderen Ereignisse. These pieces of guessed text are called cribs, which I can kind of understand if you look at the meaning of the word. Not only do we have to guess what's in the message, but we need to guess where it occurred. To make this more tricky, the Germans would sometimes front-load the message with random letters called Quatsch. One of the tricks used to locate a crib in a message was the fact that Enigma could never encode the letters itself. Here, I'm repeatedly encoding the letter A. If we look at the ciphertext that's produced, there are no A's in it. We can't see any A's at all. Let's look at Veta Forsaga Biscaya, which was the crib used to crack the settings on D-Day, which is why I've used it so much. If we look at the encrypted text, none of these letters match. But if we move it across by one letter, then we get a conflict with the S's, so we know that this can't be the position of the crib. But how much does this really help? Well, the probability of a mismatch in the first position is 25 on 26, 25 on 26 for the second position, and so forth. Indeed, the probability of any random string not overlapping with Veta Forsaga Biscaya is 25 on 26 to the power of 23, which is about 40%. It means in this case we can eliminate about 60% of the possible crib locations in the message. For a shorter crib, like Veta Forsaga, it's only 25 on 26 to the power of 16, which is 53%. So using this fact that the Enigma won't code a letter as itself cuts down the number of candidate crypt match sites by about a factor of 2. Helpful, but hardly a showstopper. Without it, we just would have needed twice as many BOMBE machines. I know this is a bit of a sacred cow, and I'll come back to this issue later. Okay, so we know from the context that we think the message is a weather forecast. We've made our best guess as to where the crib matches the ciphertext. I'm going to show the position of each letter pair, and in this case, we actually know the rotor settings for each position as well, but generally we don't. This is what we're trying to figure out. The next step is to create a mapping of the plain text to the ciphertext. This bit's done by hand. We just start laying out the connections. Remember that these mappings are symmetric between the plaintext and ciphertext, so it's the pairing that matters, not which one was plaintext and which one was ciphertext, because they map to each other in both directions for any given rotor setting. I try to match up all the letters in the crib, and I take note of where the pairings occur. This is such an important step. I'd really encourage you to go to an online Enigma emulator, generate some encrypted text, then try to generate this type of map showing the pairings. Once I've finished, I end up with a map that looks like this, and the next step is to identify the loops. I can actually see 5 loops here. Apparently, in the nomenclature of the time, these were called closures. HGRH, HGTOH, HGBSWH. The direction of the loop isn't super important at this stage. HGTVYEOH, and finally, HWAEOH. All of these go through H, so I'm going to call H my key character. This mapping is called a menu. I'm not sure why it's called that, but if anyone knows, let me know. Well, the goal is to actually determine the rotor settings from the crib and the ciphertext. It's easier to understand what's going on by following an example where the rotor settings are already known, NSX in this case. Let's focus on this simple closure, HGRH. In our original text and ciphertext, these transitions occur at positions 9, 11, and 8, which correspond to Enigma settings NSG, NSI, and NSF respectively. Remember that at each position, the letter transposition is symmetric, which means it doesn't really matter whether it's in the plain text going to the ciphertext or the ciphertext going back to the plain text. Notice that I'm only rotating the right rotor here. I'm not moving the middle rotor or left rotors, and we'll discuss this later in the video or in the next video. Now what I'm going to do is set up 3 Enigmas with rotor settings of NSG, NSI, and NSF. I press H on the NSG machine and it comes out as a G. I type G into NSI, it comes out as an R. Then an R into NSF and it comes out as an H. Hopefully this is what you were expecting. This is just setting up the Enigma machines to match our loop, and the H going in produces an H coming out. This is a key concept to understand. Now, this should be true for all other loops. HGTOH uses 4 Enigmas, with NSG, NSL, NSA, and NSE. I go through the same motion. H on the left goes to G, goes to T, goes to O, then back to H. You might be thinking, great, sure that works, but you know the plugboard settings. How does this help things? Well, let's look at the simple HGRH loop. Let's think about what's happening. We know the plugboard settings. When we type in an H on the left keyboard, it goes through the plugboard to become G. This goes into the rotors of the NSG machine and becomes H. The H goes through the plugboard and becomes G, and this goes to the lampboard. I manually type G into the second keyboard. This becomes H, and goes through the rotors with the setting NSI to become C. We go through the plugboard to become R, which is displayed on the lampboard. We manually transfer this R over to the third Enigma via the keyboard. This time, it goes through the plugboard to become a C, then into the rotors with settings NSF and comes out as G. This goes through the plugboard and becomes H. Now here's the single most important point to understanding how to crack Enigma. We have an H coming out of the rotors on the left. It goes through the plugboard to become a G, which then goes through the plugboard to become an H again. Because the plugboard pairings are symmetric, G maps to H and H maps to G. The first pass through the plugboard is cancelled out by the second pass through the plugboard. The character coming out of the left rotors will always be the same as the one going into the middle rotors. Why don't we make a machine that bypasses the plug board and connects the output of one set of rotors in the first machine to the input of the rotors on the second Enigma? It turns out that the same is true for the second set of plug boards. They cancel each other out, and we can feed the output of the second rotors directly into the third. Then, out of the third rotors, we get a G which maps back to an H. We don't even need these intermediate plug board settings because they keep cancelling each other out. We just need to guess the HG plug board setting and that's it. The same holds true for the HGTOH loop. We can just start with the one plug board setting, skip all the ones in between, and get back to an H. This should be true for the other loops, like HGBSWH and HGTVYEOH. Because these middle plug boards keep cancelling each other out, maybe we can use this to figure out the rotor settings without actually knowing the plug board settings. I'm feeling good about this. Let's write some code. I'll assume that we've guessed the correct rotor ordering. We'll call it 1, 2, 3 in this case. Then we loop through all the possible rotor settings from AAA to ZZZ. This is actually what the BOMBE's doing by rotating the drums. We advance the rotors like we did in the last video. Next, we step through all possible settings from A to Z, which is our guess for what H connects to on the plug board. I have a separate one-dimensional array for the rotor offsets for the HGRH loop, which I derived directly from our diagram. I step through the HRGH loop, offsetting the right rotor by the appropriate value. I basically pass the output of the previous rotor into the current rotor, completely bypassing the plug board. This is the single most important point. This routine doesn't need to know what the plug board settings are. The decode Enigma routine is exactly the same one I used in the last video. Once through the loop, if the letter going into the left rotor matches the one coming out the right rotor, then we display the rotor settings and the character we've matched to H on the plug board. Can we break Enigma? Let's give it a whirl. And we have 17,632 possible matches. Well, that's not good. Let's try another loop. HGTOH. 17,617 matches. What the hell? Let's give HGBSWH a try. 17,587 matches. I tried the other two loops, and I got very similar results, in the mid 17,000 range. What's going on?
My machine will work.
If we think about this more carefully, for any rotor settings throughout the loop, then for some arbitrary input value of n, the output can only be a letter from A to Z, and there'll be a 1 in 26 chance that it's n just by dumb luck. We're trying 26 by 26 by 26 rotor settings, and we make 26 guesses for the mapping to H. If we multiply this by a 1 in 26 chance of getting the same value out by dumb luck, we expect to get 17,576 matches by random, plus 1 for our correct setting. Okay, but what are the chances that two loops starting with the same input character will end with the same character both times? For a completely random system, this should be 26 by 26 by 26 rotor settings, times 26 for our guess at the mapping, times 1 on 26 for the first loop, times 1 on 26 for the second loop, which is 676 false matches and 1 true match. Let's try the HGRH loop and the HGTOH loop together. I'll change the closures array to be 2-dimensional, and I'll add in both loops. Now I need another for loop to go through all the loops, and we leave the other for loop in place which steps through the loop. If the start and end characters of a loop don't match, I set no match to be true. Let's give it a go. Ooh, 676 matches. We might be onto something here. Excellent, we're heading in the right direction, but will the trend continue? For 3 closure loops, we'd expect to see 26 to the power of 4 times 1 on 26 to the power of 3 random matches, which is 26, plus our 1 correct match. I've added in the HGBSWH loop. Let's run it again. Excellent, 31 matches. That's another massive reduction in the number of false matches. If you look carefully, you can see our known correct answer, which is NSX with H mapped to G. Alright, let's go for the big one. For 4 closure loops, we'd expect to see 26 to the power of 4 times 1 on 26 to the power of 4, which is 1 random match and 1 correct match. I've added in the HGTVYEOH loop. Will this be enough to crack Enigma? Yes, 1 match. Our known setting for this example.
Turns out that's the only German you need to know to break Enigma.
Just for completeness, I'll add in the 5th closure loop, HWAEOH. This time, we'd expect to see a random match 1 in 26 times, plus our 1 correct answer. Sure enough, we get the 1 answer. Instead of searching through 150 million possible plugboard settings, we just need to find the plugboard match for our key character, which means we only need to check 26 possible values per rotor setting. We basically need 4 or more closure loops to identify a match with a reasonable degree of confidence. We'll still occasionally get false stops, but once we had an answer, we can just manually check it against the rest of the message. We've correctly identified the rotor settings and plugboard match, but here's the really cool bit. We already know the plain text and the ciphertext for the loops, which means if we print off the letters between the rotors for our found solution, we should be able to deduce the plugboard mappings. I've added some code which displays the intermediate rotor settings. These are the letters the rotors see and produce for the loops in our solution. HGRH maps to GHCG. We already know that H maps to G, but we've discovered that R maps to C. For the next loop, we see that T maps to M and O maps to S. Let's keep going. HGBSWH maps to GHQOKG. This gives us B mapping to Q and W mapping to K. Now this one's interesting. V maps to V. So this means there's no wire connected to V on the plugboard. Same for Y. And we also discover that E maps to J. For the final loop, A maps to A. That's 7 pairs and 3 unplugged letters. What about the remaining plugboard matches? Well, this is where these extra bits of information can help. Let's look at position 17, where K is encrypted as I. We already know that K maps to W, then it goes through the rotors at NSO to become an unknown letter, and then it's finally displayed as an I. If we try an Enigma with no plugboard mapping, we see that the W becomes D. So DI must be another plugboard mapping. Similarly, A maps to A, goes through NSR, which becomes Z, and U is displayed. So ZU is another plugboard mapping. Finally, Y maps to Y, goes through NSS, which becomes X and displays as P. So XP is our final plugboard mapping. There we have it. This is the algorithm the basic BOMBE used to crack Enigma. Before I finish, I just want to revisit the idea that Enigma, not encrypting a letter as itself, was the key to cracking it. It does reduce the number of crib match sites by about half, but I thought maybe it impacts the closure loops in some way, and that's where this idea came from. While Enigma can't encode a letter as itself, I certainly can in the simulation. All I need to do is change the mappings in the reflector. Normally for the second reflector, B maps to R and R maps to B. I'm going to change this so that B maps to B and R maps to R. Okay, our new encrypted text is very similar, but we do see some matching letters. The E's at position 10, the G's at position 14, and the A's at position 20. I went through the process of generating another menu, and it's very similar to the previous one, except we have these extra loops. I found 4 obvious closures, and I modified the code for these new loops, and I ended up getting our solution and 1 false stop, which was to be expected. I tried adding in another closure that contains a repeated character, and sure enough, we got back our single solution. While I haven't performed an exhaustive analysis, I couldn't find any evidence that the Enigma coding a letter as itself significantly impacted the BOMBE's algorithm. Therefore, I think it's these closure loops and the fact that plugboard settings would cancel each other out that really was the key to cracking Enigma. From what I can tell, this observation was one of the main contributions of Alan Turing. In the next video, I'll go over how the BOMBE implemented this algorithm, and I'll design a BOMBE replica based on EPROMs. After that, we'll look at the Welshman diagonal board in more detail. If you're new to the channel, I'd encourage you to have a look at the ZX Spectrum Turing Edition playlist while waiting for the next video.